So today we're going to talk a little bit more about geometry again and some of our applications of geometry. We've looked at angles. We've talked about angles a bit. What is an angle? If I look at this and I said that is a 29-degree angle, what's that mean? What's that 29 degrees mean? Anybody know? Well, there's actually two different ways that angle can be defined. That whole 29 degrees is defined in a couple of ways. The original definition of an angle as being measured in degrees came from navigation. We had a navigational system where the east direction was 0 degrees. And as you went around the compass rose, that's east, north, west, and south. As you went around the compass, north was 90 degrees, west was 180 degrees, south was 270 degrees, and then back to east was 360 or back to 0 degrees. And an angle between two rays, as these are, was defined as the difference in their direction. So let's say I had one that went in this direction, and let's say that is at the 21 degree direction. And I had another one here. Let's say that's at the 74 degree direction. The angle between them was just the difference in their direction. 74 degrees minus 21 degrees is 53 degrees, which made that a 53 degree angle between them. Make sense? But over time, navigation has become used less and less. So they had to redefine that definition of an angle because we're no longer living in an age where a majority of the population is familiar with the concepts of navigation. At least not beyond punching it into your cell phone or your computer and having it spit out directions for you. So what they did was they just defined benchmarks. We've talked about benchmarks before and other things. A complete circle is how many degrees? 360 degrees. So a half circle is 180 degrees, turning directly into the opposite direction. And if you make a square corner, that would be 90 degrees. In fact, we usually indicate that that's 90 degrees by putting a square in the corner of it to indicate that that corner is square. So we have some special angles. We have that angle that makes a square corner, of course, 90 degrees. A special name for it is a right angle. And the one that was 180 degrees, well, yeah, a line. But if we're looking at it in terms of an angle, it's called a straight angle. All other angles outside of those standard fractions, 1/2, 1/4, or full circle, are basically a fraction of a circle. If I look at this angle and I say that it is 50 degrees, what that's saying is that that angle is 50 3/60ths of a full circle, defining 360 to be a complete circle or complete turn. So beyond just giving the angle, the degrees of an angle, our angles can be classified in categories. So we've already mentioned a couple of times the right angle. And the right angle seems to be a logical place to divide them up because we don't have too many angles that are larger than a straight line, larger than 180 degrees. So the right angle is right in the middle there, 90 degrees between 0 and 180. Things that are smaller than a right angle, like this, are called, not everybody at once, acute. Left angles, there you go. They're called acute. Think of it this way, an acute angle is smaller than a right angle. Small things are generally called acute.
Do we need to know that one?
Acute? Oh yeah.
For real?
No, I'm just kidding. Everything I've taught you this semester, just a one big joke.
Well, you said that we're not gonna need this.
I keep in my motion.
So if it's an angle that's bigger than a right angle, it's called obtuse. It's kind of a loose connection, but I always think of the word obese, and obtuse is kind of going to obese is oversized. Obtuse is over 90 degrees, larger than a right angle. Yeah. Those two terms actually have bigger meanings. You ever heard, if you talk about a psychology class, about an acute thinker? An acute thinker is someone who can get a very narrow focus on things and see the very details of a problem. They think in small, the very narrow angle. An acute angle is very narrow and small. Or an obtuse thinker. An obtuse thinker thinks at a wide angle and sees the big picture but doesn't necessarily see all the details or sees all the extra possibilities off to the sides that could come in that are not as likely. Well, being able to go from one to the other is a very unique skill. People that can step back and see the obtuse or the big picture and then focus in, it's a very unique skill. I worked in engineering for several years. Most engineers are very acute thinkers. One of the things that made me very popular, that made my career as successful as it was I was one of the people that had that ability. I could step back and see the big picture and say, wait a second, we're focusing here. If we slid over here, it would be so much easier. Well, it is, but a lot of the acute thinkers can see the details and can see the details in very, very fine resolution, but they can't step back and say, hey, wait a second, we don't need something to take this from here to here, we can just let it fall. You know, silly things like that. So anyway, we want to talk about relationships between these angles. Sometimes we have more than one angle. If we have angles that share a vertex and also one side, where the vertex is this point here where the two rays come together. They're what we call adjacent angles. And actually, in this case, there are several angles formed. Not only is there this angle and then this angle here, but there's also the larger angle formed. And then, of course, there's all the angles that could wrap around the other way and all that, too. We're going to concentrate for now on the smaller of the angles, in this case, the acute angles. And I'm going to call this angle A here and this angle B here. And this bigger one out here, angle C. And when we have adjacent angles, the advantage of them is they're additive. By additive, I mean you can add them up. If angle A here is 31 degrees and angle B here is 42 degrees, angle C is just going to be 31 plus 42, or 73 degrees.
In actuality, A plus B equals C.
Oh, in this case, yes. I could draw another case like this, where I tell you that this angle here is 116 degrees. Draw this in where I tell you this is 48 degrees, and I ask you, what's this angle here? Yeah, if they're additive, they're also subtractive. 116 minus 48, it is 68 degrees. What do you think? Still better than a sharp stick in the eye? For now? For now. We have special combinations of angles. In this combination here, if I happen to know that this angle here is 52 degrees, do I know this angle here? Yeah, what is it? What? 180 minus 52. Where did 180 come from? Yeah, because this is a straight line across here. It's half a turn or half a circle. It's 180 degrees. A straight angle. Since we know that that's a straight angle, we know then that these two angles have to add up to that. Have to add up to 180. So to find the other one, we subtract the 52 from 180 to get 128 degrees. This is what we call supplementary. Two angles, in this case the 52 and the 128, that add up to 180 degrees or a straight line are supplementary angles. So if I give you an angle is 103 degrees, and I ask you to find its supplement, what's its supplement? (180 minus 103), otherwise known as 77 degrees. Make sense? Well, we have another special benchmark that we had, the square corner, otherwise known as what? Right angle, or 90 degrees. You got it. If I drew a line in here like this and told you that this was 68 degrees, what's this angle here got to be? (22). How'd you get that? You got 90 minus 68. You got give us 22 degrees. Here we had two angles that added up to a right angle. That's what we call complementary. Two angles that add up to 90 degrees or a right angle are called complementary angles, or angles that complement each other. Now, if you're anything like me, when I learned these, I could remember the two terms, but for a while I had a hard time keeping straight which one was which. The little trick that learns for me, you get complements when you are right. So complements are right, add up to right angles. So find the complement of 27 degrees. What am I going to do? (90 minus 27 is 63 degrees is the complement. How are we doing so far? Yes? No? Nobody cares? Here's the one that Cody was thinking about before, I'm sure. That angle is 43 degrees. Can I find this one over here? 43 degrees. Why? Because they're the exact same angle. How do we know they're the exact same angle? Well, common sense would tell us if we have this line and we rotate it to make that one, that's rotate the same amount over here, correct? That's kind of the common sense viewpoint. But let's look at a little bit more of a brute force math viewpoint. What does this angle here have to be? 137. Why? Yeah, because that's a straight line. Those two have to add up to 180. If that's 137, however, this is also a straight line. So those two have to add up to 180. Which makes this one 43. These two angles here and here, and of course there'd be a pair of them here and here as well, are what we call vertical angles. They're formed by the same rotation of two lines, and those two angles must be equal. So now with the rules that we have seen here, I wanted to find some relationships between a couple of lines, and then we'll go another step further. We can have two lines that intersect like this. They make a right angle. In fact, there's a stronger term in geometry that's sometimes used called perpendicular. Now you might say, well, why do we need that word perpendicular? We can just say the two lines intersect at a right angle. When we're working on a sheet of paper like this, geometry becomes two-dimensional. But in real life, geometry is three-dimensional. Perpendicular is required to define things in three dimensions. What perpendicular means is, let's say you have a sheet of paper and you stick your pencil up through that sheet of paper. For that pencil to be perpendicular to the sheet of paper, it has to form a right angle with the paper in every direction. No matter what direction you measure the angle in, it forms a right angle with the paper. That's perpendicular. It's a right angle in every possible direction. So we have two lines that are perpendicular. They intersect, and then not only do they intersect at a right angle, but they form four right angles. Because, of course, from what we just learned, this angle here and this one over here have to be the same because they're vertical angles. These two have to add up to 180, so 180 minus 90 makes another 90. If they form one right angle, they form four of them. Next relationship we have looks like this. What's that relationship there? Parallel. What's the definition of parallel? What's that? Well, a lot of people have been told the definition, parallel lines never do what? Never cross, never intersect. Which, again, 2 dimensions on a sheet of paper, that's adequate. But in 3 dimensions, let's say this is a line and this is a line, do they intersect? No, they don't intersect. But are they parallel? No. So in 3 dimensions, just because they don't intersect does not necessarily mean they're parallel. So there is a stronger definition for parallel. Well, side by side, not necessarily. I mean, it kind of is, but the definition that is used, the technical definition is everywhere equidistant. In other words, what that means is always the same distance apart. Now, distance between lines is found by picking a point on one line, and then from that line drawing a line perpendicular to the other one. And the length of that line is the distance between them. Distance is always measured in perpendiculars. How would you describe the relationship between these lines? Messed up. Well, they intersect, right? So you can say they're intersecting. Well, they form some vertical angles. They are intersecting lines, but intersecting lines can be perpendicular. These lines are not perpendicular. So to state that they are intersecting but not perpendicular, the term we use is oblique. They may intersect, but they're not right. They don't make a right angle. So when I use the term oblique to describe Cody, that's what I mean. He's just not right. Sorry, Cody. Yes, that is in the recording for later, too, so if you need to use it against me, you can. But we've already discussed some of the things with those oblique intersecting lines. Let's say we have 138 degrees here. What's this angle over here? This one here.
Really?
I'm waiting.
Subtract it from 180.
Uh-huh. 42 degrees. There we go. How about this one down here? 138. Very good. Anybody want to guess this one over here? 42. There we go. So these two lines here are obviously parallel. I cut across those with another line. That other line is what we call a transversal. And I'm going to give you this angle right here. of 67 degrees. Can I find this angle over here? 67. Why? They're vertical angles, right? How about this one up here? 113. Where'd that come from? 180 minus the 67. Good. This one down here? Also 113. We've seen this before. When two lines cross, there's really only two different angles formed. There's four angles formed, but they're in pairs. There's only two different measurements. What can I do down here at this intersection? Well, this line here, if we moved it, would fall exactly on top of that other one, right? Those angles would fall exactly on top of each other. So what does that mean for this angle right here compared to this one? Has to be 67. They're the same angle. They just got slid over to the parallel line. So that means this one here is 113. This one is 67. And this one is 113. Now, if this were a formal geometry class, which it isn't, and I don't want it to be, because formal geometry has a lot of terminology in it that we don't want to get into. Formal geometry has a very good place. It's a great way of learning logic and visualization and stuff like that. Not our purpose in this classroom. But in a formal geometry class, you would define all sorts of angle relationships here, like corresponding angles. These two would be corresponding angles. Alternate interior angles. These would be alternate interior angles. Well, so would these two. Alternate exterior angles would be those two or these two. Corresponding interior angles and all sorts. You'd have alternate exterior angles are equal. Alternate interior angles are equal. Corresponding interior angles are supplementary. Stuff like that. Rather than defining all those different rules and all that different vocabulary, we're going to define Hoff's rule. And what my rule is, and write this down, it will be on the test, and you are expected to spread this around to all your friends. Hoff's rule is, when you have parallel lines cut by a transversal, all angles are either equal or supplementary. And it should be relatively easy to tell, because that transversal, when it cuts here, it's going to form two angles here and here. One of them, unless that transversal hits it perpendicular at a right angle, one of them should be acute and one of them should be obtuse. So there you can know all the angles in this thing that are obtuse have to be the same. All the ones that are acute have to be the same. And if there's one of each, they have to be supplementary. So let's practice that. And let's say that I give you this angle here, 55 degrees. I want you to find angle 1, 2, 3, 4, 5, 6, and 7. Angle 7? What's that? Not 100. This is not a 1 here. That's the angle. That's just 55 degrees. This is 125 degrees. Good. 2 would be just 55. This would be 125. This would be 55. This would be 125. This would be 55. And this would be 125. For being 7 questions, it's kind of a boring problem, isn't it? Another relationship in these angles, if we have a triangle, the angles within a triangle must add up to, careful, to call this one 52 degrees, 61 degrees, 67 degrees. Those angles must add up to 180 degrees. Every triangle, the angles will add up to 180 degrees. You can see 180 is kind of an important number to us in geometry. It's a straight line, it's any pair of angles that add up to a straight line, but it's also a triangle. So if I have this set up here, and I tell you that this angle here is 49 degrees, and that this angle here is 127 degrees, and I ask you to find this angle right here. What is it? How do I find it? What can I do? Do I know this angle? What is it? What is it? 49. Because it's got to be the same as that one, right? Do I know this angle here? Not 127, but 180 minus 127. Give it 53 degrees. Those two don't have to be equal. Those two add up to a straight line, so they add up to 180. Now how about this one? Perfect. 53 and 49 make 102. 180 minus 102 is 78 degrees. Good stuff? For now. Sure. Ready? Find this angle right here for me. Well, this angle here I know really quickly is what? What is it? SB 47. This angle and this angle have to be the same because this here is a transversal on parallel lines. This angle would have to be the same as this one here. I can find that one by doing what? Subtracting. 180 minus 123 gives me 57 degrees, making this one 57 degrees. Now what? You got it. 57 plus 47 is 114. Or not 114, 104. 180 minus 104 is 76 degrees. Good stuff?
Oh, wow.
It sucks. All right, we're going to take a little bit of a break there. Let's take 10 minutes. Come back at 9:10. We'll start up again.